Hello and welcome to our physical sciences session. My name is Temba. Today we shall take a look at revising some of the most important aspects on redox reaction in terms of the technique of responding to questions, how you approach the multiple choice, how you use the standard reduction potential tables. At the end of the day, we must get to a point where we are actually comfortable. So this session actually focuses on the revision part of our redox reactions, right? Okay, so in as far as the chemical change is concerned, we by now know that in a redox reaction, there is both oxidation and reduction, and the substances that are involved in the transfer of these electrons, it's your oxidizing agent, which loses, as well as your reducing agent, which gains. And then we can keep track of a redox reaction in terms of the change in oxidation number of a particular substance in terms of the loss as well as the gain. Right. Okay, so some of the terminology, as I've indicated, we'll talk about redox, your oxidation, your reduction, which are actually processes, which involves the transfer of electrons, and we shall use oxidation numbers to actually keep track of as to whether a substance gains or loses electrons. Right. Multiple choice is one of the very important skills, that you need to develop. And for us to be able to be comfortable or understand the technique in as far as, approaching these multiple choice, we need to expose ourselves to as much practice as we possibly can. In this example, we are given a reaction between ammonia and oxidation, right? And oxygen, which is an oxidation reaction. But in this question, the question says, which atom has an oxidation number of -3, right? Now, remember, there are rules in as far as oxidation numbers are concerned. And if you are given 4 possible options, it's very important that you identify what you think of in terms of distractors. But for you to identify the distractors in a multiple choice type of a problem, you need to understand, or you need to know your stuff. Okay, now this appeals to the rules of assigning oxidation numbers, right? So in this case, we want to identify an atom or a substance that has an oxidation number of -3. Now, let's take out those that have nothing to do with that. For argument's sake, if you look at oxygen as a molecule of an element, the rule says that if it's a molecule of an element or an atom of an element, the oxidation number is 0. So the oxygen in the oxygen in the oxygen molecule, if for lack of a better word, has 0. And then if we look at, say for argument's sake, in ammonia, we know that hydrogen always is +1. Okay, so if there's 3 of them, so if hydrogen is +1, it means then the nitrogen is -3, because the net in this case is actually 0. So if you add the oxidation number, the total of hydrogen and nitrogen, we must get 0. So there's 3 of hydrogen, meaning that in this case, the nitrogen in ammonia has an oxidation number of -3. But we can also try and verify that by looking at nitric oxide, which is a nitrogen monoxide. Oxygen in its combined form, it's -2. Then it means in this compound, nitrogen is +2, right? Hydrogen in its combined form is +1. There's 2 of them, so that the total is 0, then the oxygen is -2. So it means then our solution becomes the nitrogen in ammonia, right? Okay, and then the key terms, again, we talk about substances. Now, these substances are your oxidizing agent, your reducing agent, your spectator ions. So your oxidizing agent undergoes reduction, a process of reduction, while a reducing agent undergoes a process of oxidation. So this undergoes reduction, okay? And then this one undergoes oxidation, right? Okay. And then in the follow-up question, very same equation of reaction, identify the reducing agent. What is a reducing agent? It's a substance that undergoes oxidation. So let's keep track in terms of the oxidation numbers. Now, we agreed that nitrogen in ammonia is -3, right? And then the nitrogen in nitric oxide is +2, right? It's +2, right? Now, what a reducing agent actually undergoes oxidation. So when oxidation occurs, what happens to that particular substance which undergoes that process? Its oxidation number needs to increase. So it becomes more positive, or you can think of it in terms of becoming less negative, okay, depending on what you are given. So a change in oxidation number from -3 to +2 is an increase in terms of the oxidation number. So a substance that actually undergoes an increase in oxidation number becomes your reducing agent because it undergoes oxidation. Right. So in this case, the nitrogen in ammonia is actually our reducing agent because we are keeping track of the change in oxidation number. But to arrive at that, we actually need to understand our stuff, that the reducing agent is a specific type of a species or a substance. It could be an atom, it could be an ion that undergoes a process. The process involved in this case is oxidation, which has to do with loss of electrons, right? Okay, so we are happy to say that the nitrogen in ammonia, it's not the ammonia, it's actually the nitrogen in ammonia. So it's very important, again, to ask ourselves, after selecting the possible answer, to say, what did the question say? And you ask yourself a follow-up question to say, have I actually answered the question? So it's not the ammonia that is a reducing agent. It's actually the nitrogen in that compound which undergoes oxidation. For that reason, it is a reducing agent. Right. Okay. Okay, and then we are given another reaction, which is a redox reaction. Okay. Now, we are also asked that we need to identify the role of ion 3 in this reaction. Again, when you talk about, the keeping track of the changes in oxidation numbers, we are saying that we are able to say whether a substance underwent loss or gain. All right, let's look at ion 3. Okay, we can immediately extract ion 3 in terms of what its state on the left-hand side of the equation compared to what happens to it on the right-hand side. So we've got Fe3+, which is ion 3. Okay, it becomes ion 2. Okay, there's only one thing that can happen. Has the oxidation number increased or decreased? It has decreased. It simply means that the ion 3 gained an electron. Okay, so the gain of electron has to do with the reduction half reaction. So what is a substance that, this is the substance that undergoes the gain of electrons. Now, it goes back again to the terminology. So the one that accepts electrons, in this case, this is what is happening to ion 3. So in other words, we can think of ion 3 as an oxidizing agent. Okay. So the role of ion in this case is that it is an oxidizing agent. And an oxidizing agent, in terms of the electron transfer, it is actually an electron acceptor, right? So it's neither a spectator. What is a spectator? Again, a spectator, remember, is those species that are not directly involved or not involved at all in the transfer of electrons. So these are some of the, little ideas that you need to bring to the fore in terms of, the technique of responding to multiple choice problems. Let's take a short break for now. We'll look at more examples in as far as revising redox reactions. See you after the break. Welcome back. We're still doing a revision on redox reactions. Now we are able to represent redox reaction. But in a given example, there are certain techniques also that we need to kind of master. So let's look at the next set of examples and see how best we apply what we've learned. Right. So the equation below represents a redox reaction. Immediately we're thinking there is transfer of electrons, there is loss as well as gain between two substances that are reacting. So in this redox reaction, there is 8 grams, that's the mass of iron 3 oxide. The formula is given. The iron 3 oxide reacts with 3.8 grams of aluminium. Right, so the balanced equation of reaction is already given to us. So this is the equation that we shall focus our attention on. Right, now the first question says, assign oxidation numbers to all the elements in this reaction. Now immediately we recognize that this question is about us going back and reminding ourselves of what is exactly important in as far as the rules that we pay attention to when we assign oxidation numbers. There's a whole set of rules that we need to remember and know when to apply each one of them in given scenarios. So in this case, we are going to assign, let's start with iron 3 oxide. Now, which rule applies in this case? We know that oxygen in its combined form, the unit oxidation number is -2, right? So here oxygen is -2, right? But the total is -6 for oxygen, right? And then for iron in this case, because of that chemical formula, is +3, right? It's +3, the total is +6, which gives us a total of 0 for that. Okay. Now, if we focus our attention on aluminium, in its purest form, any pure substance as an element, it has an oxidation number of 0, right? Let's look at aluminium oxide. We apply the same rule in aluminium oxide, 3 oxide, as in iron 3, right? In oxygen, in its combined form, it's -2, right? Now, the unit oxidation number of oxygen is -2. Then for oxygen, the total is -6, right? So in this case, iron is +3, all right? Meaning the total, because there's 2 atoms of aluminium, is +6. So if you say +6 minus 6, it gives us a total of 0 for this compound. And then iron as a pure substance, which is an element, then it has an oxidation number of 0. So these are the different rules that we definitely want to apply in as far as oxidation numbers. Now immediately one thinks, why is this important? Why are these rules important? For us to keep track of changes in oxidation number of a particular substance in a reaction, we are able to understand whether that substance undergoes loss or gain of electrons in as far as the transfer in the context of redox reactions. Right. Okay. Now the follow-up question says, write down the oxidation half reaction. So oxidation involves loss of electrons. So we know that iron here is +3, oxygen is -2 in its combined form. This one is 0, +3, -2, that is 0. So when oxidation takes place, the substance actually loses electrons and there is an increase in the oxidation number. So if you look at, for argument's sake, aluminium. Aluminium initially, it has an oxidation number of 0 and then it changes to +3. What has happened to aluminium? Aluminium has lost electrons. And then how do we represent this half reaction? It's going to be aluminium, okay, metal, to give us aluminium, okay, 3 plus 3 electrons, right? So this is the substance that loses, okay? So what this substance has undergone is oxidation, which is the loss of electrons. And immediately we're thinking in terms of language, this substance is actually our reducing agent. So in other words, we are saying aluminium is a stronger reducing agent, okay? Because what aluminium has done here, it has displaced iron in the oxide, okay? So we are saying aluminium is a stronger reducing agent. So that's straightforward, right? Okay, and then write down the reduction half reaction. So in the background of aluminium displacing iron, okay, we are saying that what happens to iron? Iron then actually gains electrons in the process. And the process of gaining electrons can be represented in the form of a reduction half reaction. Exactly how do we do that? Right, we are saying that if we look at iron, here iron is +3, okay? On the other end, it's 0. So what has happened to the oxidation number of iron? It has decreased, right? Or it has become less positive, if you want to think of it that way. So how do we represent that in terms of the half reaction? We are saying that iron 3, okay, plus 3 electrons, okay, it gives us iron. All right? So what has happened to the iron 3? The iron 3 ion is the one that undergoes reduction or the gain of electrons. So what name do we give to the substance that undergoes reduction? We call it an oxidizing agent. Okay, something of particular interest to us now is to understand that to say iron undergoes reduction, it's not entirely true. Actually, it's the iron 3 plus ion that gains the electron. So to say ion, you are referring to the atom of iron, which is a misrepresentation of what exactly is happening. So pay careful attention to the actual species. The question may ask in terms of the formula or the name, or it could be both, formula and name. You need to pay careful attention to those keywords. Right. Okay, so this is the reduction half reaction. Okay, so in the above redox reaction, identify the oxidizing agent and the reducing agent. So we have done that. We said the aluminium undergoes the loss of electrons. Okay, so if we say aluminium is a reducing agent, we are saying aluminium undergoes oxidation. So it's the aluminium atoms or metal aluminium that undergoes oxidation, right? And then an oxidizing agent undergoes reduction. So what is reduced is actually the iron 3 plus ions. So be careful of that. So these are the formulae of the reducing agent and the oxidizing agent. So aluminium is the reducing agent because it loses. Iron 3 ions are the oxidizing agent because it gains electrons. So that's very, very important as well. Now, stoichiometry is, one part of chemistry that is very, very broad, and it's very important for us to emphasize that it can be anywhere where there is a reaction. We can talk about stoichiometry in terms of, the mole concept. Understand the importance of the mole as the SI unit of quantity of matter. So everything is about the mole, because a mole of any substance contains the same number of particles. So as a way of measuring quantity of matter in a chemical change, we talk about the mole. Okay, so as long as there is a reaction, we can allude or talk about the stoichiometry involved in that chemical change. So in this example, we've got 8 grams of iron 3 oxide as well as 3.8 grams of aluminium. So the reaction runs to completion. What does that mean? It says that this reaction occurs to a point where it stopped. Whether the aluminium was used up or the iron 3 was used up, it doesn't matter. But one of the two reactants reacted completely. So the question demands that we determine the percentage yield given the mass of iron that was formed. Right. So first things first, the equation of reaction is balanced for us. So the stoichiometric ratio in which these react is that 1 mole of iron 3 oxide reacts with 2 moles of aluminium to give us a mole of aluminium oxide and a mole of iron. So the stoichiometric ratio, in short, is 1:2:1:1. Right. Now let's ask ourselves, in 3.8 grams of aluminium, how many moles are present? So number of moles of aluminium, okay, is equals to mass of sample of aluminium over molar mass of aluminium. So what do we have there? It's going to be 3.8 grams, okay, divided by the molar atomic mass of aluminium is 27, right? Okay, in this question, it says here, the equation below represents a redox reaction that has a lot to do with the transfer of electrons. There is 8 grams of iron 3 oxide that reacts with 3.8 grams of aluminium according to the balanced equation of reaction. So this reaction runs to completion. It means one of the 2 reactants actually gets used up, and then the reaction stops for that reason. So we want to determine the percentage yield given that 4.76 grams of iron was formed, right? So what is important here is to understand that the stoichiometric ratio in which these substances react from the balanced equation is it's actually 1, okay? Just to correct that, right? It's actually 1 is to 2 is to 1 is to 2. So in terms of stoichiometry, this has to do with the mole concept in terms of the quantity of matter as an SI unit. So we ask ourselves how many moles of aluminium are present in the 3.8 gram sample. So number of moles of aluminium is equals to mass of aluminium over molar mass. So the mass is 3.8 grams divided by the molar mass of aluminium, which is actually 27 grams per mole. So how many moles of aluminium do we have in this case? We can quickly go to our calculator, all right? What do we have? We've got 3.8, all right, divided by 27, all right? So in this sample, there's actually 0.14 moles of aluminium. So 0.14 mole, right? Equally so, we want to ask ourselves, how many moles of iron 3 oxide are present in 8 grams? So we are saying moles of iron 3 oxide, right, present is equals to mass of the sample, which is 8 grams, divided by 160, which you get from the periodic table. So how many moles is that? So if we are to calculate that, we've got 8 divided by 160. Okay, this actually gives us 0.05 moles, right? So this is 0.05 moles, right? So if 1 reacts with 2, it says to us that the aluminium oxide is actually our limiting reagent. So all the 8 grams of aluminium will react, right? So 1 mole of aluminium oxide of iron oxide gives us 2 moles. So the number of moles of iron that will be formed is equals to mass over molar mass. So what is the mass that we are looking for? We're actually looking for the mass of iron. So if there is double the number, if 1 produces 2, so in other words, we'll have 0.05 times 2, which is 0.1 mole, okay, is equals to what mass will be produced. What is the molar mass of iron? It's 56, right? So what mass will be produced in this case? We can go to our calculator and say 0.1 multiplied by 56, which is the molar mass. This gives us 5.6. So 5.6 grams theoretically must be produced, right? But we are told instead that 4.76 grams of iron was produced. So percentage purity, okay, is equals to, actual yield, okay, divided by theoretical, okay. We multiply this by 100, okay. So the actual one that was obtained is 4.76. 4.76 divided by the theoretical, which is expected, which is 5.6. We multiply this by 100, we'll get the percentage purity. So if we go to our calculator, okay, what do we have? We've got 4.76, which is what was actually formed, divided by what we expected from the stoichiometric ratio, which is the theoretical, which is 5.6. Okay, then we multiply that by 100. This is going to give us the percentage purity. So our percentage purity in this case, actually that's 5.6. If we can quickly go back and correct that. So that's 5.6, right? Okay, this gives us 85% purity, right? So this is 85% purity. It means then, in this sample of iron, it means that 15% of this sample contains impurities, right? So the long and short of it is that as far as the stoichiometric problems are concerned, let's pay attention to the fact that if the equation is balanced, what does that tell us? It tells us the stoichiometric ratio in which these substances actually react with each other, right? And then the whole stoichiometry comes in because this is a chemical change or a chemical reaction wherein new substances are formed. And the mole concept, how does it fit into this? We understand that the mole is actually the SI unit of the quantity of matter. So we don't talk grams, kilograms, tons when we talk amount of matter in a chemical reaction, but we talk of the moles, which is why we always go back to the formula, number of moles is equals to mass over molar mass. So this is just one of the examples to say that stoichiometry, as long as there is a chemical change or a chemical reaction, it will always be featured, right? So if we are to kind of analyze the whole idea of this problem, we are saying that if the stoichiometric ratio is 1:2, it means a mole of iron 2 oxide produces double the number of moles, which enables us to get the mass of iron theoretically that we are actually expected. So this is what is expected, okay? This is what is expected, right? But in reality, this was formed. So this is the actual yield. This is the actual yield, right? So these are some of the, the ideas that must obviously come to mind, right? For now, we'll take a short break and look at more examples after the break. See you shortly. Welcome back. We're still looking at revising redox reactions. We shall look at a couple of more examples and see how best we apply what we learned in terms of the redox reactions. All right, so at the back of our mind, we also need to remind ourselves of what is important in terms of representing, these redox reactions. In representing redox reactions, we need to have two half reactions, okay, which is the oxidation, okay, which has to do with the loss of electrons, as well as the reduction. So we call these half reactions, okay? And then the net ionic equation excludes the spectators. But what are spectators? These are species or substances that are not involved in the transfer of electrons or in the redox reaction for that matter, okay? And then a full balanced chemical equation is a combination of the two half reactions. That's in as far as representing these redox reactions. Right. Now, when it comes to balancing, what are some of the important points to remember? First of all, we must keep track of the oxidation numbers by applying the rules of assigning oxidation numbers to substances, in a reaction. And also, half reactions are actually derived. We can take them from the standard reduction potential tables. But on that note, remember, when we talk about the standard reduction potential tables, all these reactions are written in the form of gain of electrons. So by comparison, depending on the two substances that we are actually focusing our attention on, we can then decide from that point as to which one is a stronger reducing agent as well as which one is a stronger oxidizing agent. Then we are able to extract what we refer to as those two half reactions in terms of oxidation as well as reduction. Right. So the importance of the standard table of standard reduction potential table cannot be overemphasized, therefore. Right. So here is another typical question which says, consider the redox reaction which is given below. So the moment it says a redox, let's think of it in terms of electron transfer. Right. Okay. Let's think of it in terms of electron transfer or transfer of electron, which has to do with loss as well as the gain of electron. Okay, so that schematic representation becomes very, very key. So it says here, write down the formula. I'm going to underline the term formula of the reducing agent. First thing first, we need to understand what is the role of a reducing agent in a redox reaction. But by so doing, we need to keep track of the oxidation numbers. So iron 3 is 3 plus, is plus 3. Zinc as an atom, it's 0. This side ion is 2 plus, okay? And then zinc is also 2 plus. So a reducing agent is actually a substance that undergoes the loss of electrons, oxidation. So there needs to be an increase in the oxidation number, right? So a substance that undergoes the loss in this case is zinc. So the zinc metal, according to the equation, Zn, okay, to give us Zn 2 plus, plus 2 electrons. So this is the substance that loses electrons. It is a reducing agent because it underwent oxidation. So the formula, therefore, is zinc Zn, right? So sometimes it can say the name. If it says the name, then you have to write the full chemical name. But in this case, we're looking at the formula, right? Okay, and then write down the equation of the reduction half reaction. Okay, reduction has to do with the gain of electrons. So if a substance gains electrons, what happens to its oxidation number? We have said zinc loses, meaning that the other species, which is iron 3, which changes its oxidation number to plus 3, from plus 3 to plus 2. So there is a decrease in the oxidation number. Hence, this substance has gained. So the half reaction that's relevant is going to be iron 3, okay, plus an electron to give us what? Iron 2. Okay? So this is the equation. But the substance that undergoes the reduction process in this case is iron 3. Right. Pay careful attention to that. Okay? Now, the question goes on and says, write down the equation once again of the oxidation half reaction. So the equation represents a process in which substances either lose or gain in the entire transfer of electrons. So you'd want to understand it in that way. So a substance that undergoes oxidation actually has its oxidation number increasing, okay? Because that is coupled by the loss of electrons. Exactly how do we represent that? We are saying that for oxidation, we want a substance whose oxidation number increases. We have identified that zinc, according to the laws of assigning oxidation numbers, as an atom, it's got 0 oxidation number, then here it's plus 2, right? So what has happened here? Zinc has lost electrons. But then how do we represent that? Because that's what the question demands of us. We are saying it's Zn, okay, to give us what? Zinc, okay, let's just correct that. Okay. So be careful when you write, the chemical formula must be correct as well. So this is zinc 2 plus 2 electrons. So you realize that we are consistent, that in the oxidation half reaction, the electrons are always on the right-hand side of the arrow, right? So this is what represents the oxidation half reaction, right? And then use the two half reactions to write a balanced net ionic equation. Emphasis in this case is on the balance, right? So if we go to our two half equations, what do we have? We have identified that for iron to be reduced, its oxidation number, it changed from plus 3 to plus 2. It means it gained electrons. Hence, it can be explained with respect to the reduction half reaction. While zinc, if we keep track of the changes that happened in terms of the oxidation number, it's 0 to plus 2, right? So what exactly happens to zinc atoms? Zinc atoms were involved in the loss of electrons, which can be represented using the oxidation half reaction. Right, so the loss of electrons, its oxidation, gain of electrons is reduction. But remember, if a transfer does take place, whatever species A loses is the same number of electrons that species B will gain in the case of electrons being transferred between A and B. So in this case, the number of electrons lost by zinc atoms must be equal to the number of electrons that are gained by the ion 3 ions, okay, in that transfer. That's the long and short of it. So in this case, to actually balance the electrons, it says this one will multiply by 1 and this one will multiply by 2. So you'd realize once we do that, we are able to eliminate, in a way, the electrons such that it will have the same number of what? Of electrons in terms of loss and gain. So if we multiply zinc by 1, we'll have zinc, okay, plus, okay, 2 Fe3 plus. Remember, we're multiplying the reduction half reaction by 2, right? Plus, this will give us, because the electrons will be the same, 2 for oxidation and 2 for reduction. So we can kind of eliminate them. So if we multiply this by 2, it becomes 2, 2, 2. And then we are able to take that out, okay? That's why we don't, in the net ionic equation, we don't include the electrons. Then this gives us zinc, 2 plus, right, plus 2 ion 2, right? So this is our overall, or the net ionic equation in as far as this is concerned. So there's a lot of knowledge that we need to remind ourselves before we actually arrive at a solution. Oxidation numbers, the rules for assigning oxidation numbers, the half reactions, and the technique, because this particular question focuses on the balancing part of it, which is a very a critical component of redox reactions. Right. So having said that, I think we are able to then say, okay, there is quite a lot of examples, but this was just but one of the few that we have time to actually attempt. Right. For now, we'll take a short break, and then after that, we are able to look at even more examples. Let's take a short break for now. Welcome back to our session. We are still looking at revising redox reactions, but now we'll focus our attention on specific problems that actually demand that we apply the standard reduction potential tables and see how exactly we actually go to do that. So it's more about the technique. So we're not going to memorize the table, but what we're going to do, we'll actually try and understand how we apply the table of standard reduction potentials. In this question, it says the two unbalanced, I'm going to underline that because that's very, very important, equations for reactions involving sulfur dioxide are given, right? So there are two reactions here, okay? There's reaction 1, okay, where sulfur dioxide reacts with hydrogen sulfide, and in the second one, where sulfur dioxide reacts with potassium permanganate, right? Now, it says here, what is the oxidation number? So this is about oxidation number of manganese in manganese sulfate and in potassium permanganate. So this is about chemical formula as well. But because focus is on oxidation numbers, this takes us to the rules of assigning oxidation numbers. So in manganese sulfate, here we are. We know that the total of a compound, which is a pure substance, is equals to 0, right? So if the total is 0 in this case, let's let's use the oxygen, which has got a unit of -2, unit oxidation number of -2, right? So if there's 4 atoms per formula unit there, then it means the total for oxygen is -8, right? And then potassium, as a group 1 alkali metal, it is in its combined state. It has got an oxidation number, a unit oxidation number of +1, right? So then what is the oxidation number of manganese in this case, if the total is 0. So we are saying that plus 1 minus 8, what is it? So we need to find the one for manganese in this case, right? So if oxygen is negative 8 and then potassium is plus 1, we're asking ourselves what is the oxidation number of manganese in this case. One would say, okay, let it be X, okay, whatever that is, all right? So if that's the case, it means here this X is actually plus 7. So because where is the 7 coming from? So if we say 1 plus this X minus 8 is equals to 0, okay, you'll get negative 7, which is X is equals to plus 7. So in potassium permanganate, the oxidation number of manganese is equals to plus 7. Okay, what about in the manganese sulfate, which is MnSO4? Again, the total is 0. Okay, oxygen negative 2, right? Sulfur is plus 2 in this case. So if we have that, we are saying that oxygen, in terms of oxygen, negative 2 multiplied by 4 of those atoms, which is negative 8, right? And then sulfur is always 2 minus, okay, which is negative 2 or plus 2 rather, okay, because oxygen is negative 8, and then manganese is what we don't know. Now let's look at the oxidation number of manganese in manganese sulfate, right? We're going to apply the same rules of assigning, oxidation numbers. Now, the total in this pure substance, which is a compound, is equals to 0. And what do we know? In terms of oxygen, the unit oxidation number is minus 2, right? It's minus 2. So there is 4 of those oxygen, so hence the total for oxygen becomes negative 8, right? So it should give us a total of 0. But sulfur is going to be plus 2, right? Plus 2 in its combined state. Now we are looking for the oxidation number of manganese. So let that be X, right? So if that's the case, what are we saying here? What we have in this case, our X, which is the oxidation number of manganese. There's only one atom of manganese in this case. So this gives us minus 6. Then it will be plus 6 on the other end. Okay, so in manganese sulfate, this is plus 6, but in potassium permanganate, it's plus 7. So what has happened to manganese in this case? It is actually gained electrons because it changed from plus 7 rather, to plus 6, okay, according to the equation of the reaction, right? Okay, now is manganese oxidized or reduced? So what do we have here? We agreed that if we can quickly go back, in potassium permanganate is plus 7, right? In potassium permanganate, manganese is plus 7, but in manganese sulfate is plus 6. What has happened here? The oxidation number has decreased. So manganese is actually reduced. So what has happened to manganese? If we can represent this, we can say manganese 7 plus 7, okay, right, plus an electron to give us what? Manganese 6 plus, okay? Or plus 6, okay. So in this case, it says it has been reduced because it has gained electrons, right? Okay. Now, having said that, we can then move into the next question, which says, write down the oxidation half reaction for reaction 1. So oxidation in this case has to do with the loss of electrons. Right, let's look at, in this case, what is happening. Sulfur dioxide, in sulfur dioxide, oxygen is minus 2, and then here, this one is plus 2, okay? So in this case, sulfur is plus 4. If we can determine that it's plus 4 in this combined state, and then here it's 0, okay? So oxidation has to do with loss. But again, this sulfur, in this case, is if this unit hydrogen is plus 1, and then this means it's plus 2, right? So if you look at the +2 to 0, that is the gain. But if we look at from +4 to 0, again, it shows that there was actually gain of electrons. Now we ask ourselves, which of the substances are actually are involved in oxidation? And oxidation has to do with loss of electrons. So that's the main idea. So in terms of responding to this question, you must understand that you need to highlight the key words. So oxidation has to do with the loss. So the half reaction that we're going to come up with actually involves the loss of electrons, right? So these are just some of the skills that are very important. And then it says here, use the table of standard reduction potentials and write balanced net ionic equations for reaction 1. Show the half reactions. So we need to draw our attention to the standard reduction potential tables, okay? So we need to identify the correct reaction. So in this case, we are saying we need the sulfur to be one of the products, and sulfur dioxide needs to be one of the reactants on the left. So this is the overall reaction. So this is the net ionic reaction. So the question wants us to use the table of standard reduction potentials to actually determine. So which equation are we going to use? We need to go back to our table of standard reduction potentials and identify the relevant one. So this is the first part of the table, and then in the second part we have these which has to do with sulfur dioxide. It's very important to analyze the equation first before you actually write the correct one. So this is the table which will always be given in an exam. So if you draw your attention to the table, it will take you to these half reactions. So if these are the reactions, we need to identify the correct one, right? In this case, water is a product, right? And sulfur is one of them. So if we go in this reaction, we try and choose the correct one. It should involve sulfur dioxide as one of them. So I'll take that as a reduction half reaction because there is sulfur dioxide, okay? And then, but sulfur dioxide goes with which one? It has to do with this one that has to do with hydrogen sulfide. So it means if we go that way, we are able to say, okay, hydrogen sulfide is actually our reducing agent, okay? So what does a reducing agent do in a reaction? It actually undergoes oxidation. So if we are going to represent this half reaction, we'll have hydrogen sulfide, right, giving us sulfur, okay, plus hydrogen ions, plus 2 electrons. Take note, the arrow goes from left to right. It's no longer the reversible one because we've decided that this is our strongest reducing agent as per the table. And then on our reduction half reaction, we still maintain that because sulfur dioxide is one of the reactants according to this overall reaction, we are saying that sulfur dioxide in an acidic medium, 4 hydrogen ions, protons, or ions if you choose to look at it, 4 electrons, okay, to give us what? Sulfur plus 2 water molecules. Right. So in terms of balancing, we need to pay careful attention to the number of electrons. So the number of electrons lost must equal the number of electrons gained. So the ratio is 1 is to 2. So we'll multiply this one by 2 and then the reduction one by 1 so that we have 4 electrons lost and 4 electrons gained. So if we have 4, these will cancel out each other because we've multiplied by the 2. Take note. And then what are we saying? If we multiply this by 2, it's going to be 2 hydrogen sulfide, right? Plus sulfur dioxide, okay? Plus, on the left, we'll have 4, okay? And then hydrogen ions and 4 on the right because we'll multiply 2 by that 2. So these will actually take care of each other. So we can remove the hydrogen ions. They won't be part of the equation overall because we've managed to take care in terms of the balancing. Right, so if that is the case, what do we have? We've got 2 atoms of sulfur, moles of sulfur, okay, plus, okay, in this case, we will also have water, which is multiplied by 1, okay? So we'll have 2 moles of water. Right, so this is our balanced equation as per, our reaction. So that's how exactly we use the table of standard reduction potentials to actually balance. But a lot happens in terms of the rules, right? So having said that, if I can quickly go back to that, you'll realize that this is the redox reaction, but this redox reaction is based on these 2 half reactions. And then we use the table of standard reduction potential to actually identify as to which substance is a stronger reducing agent while the other one becomes a stronger oxidizing agent. That's exactly how we apply these rules. But that said, we need to understand that when it comes to application and understanding, we need to expose ourselves to as much practice as we possibly can. But what we did is just to look at a few examples, because in terms of application, the practice becomes, a very important component of our understanding. So as a result of that, the more practice we do, the more comfortable we become in as far as the redox or any other, topic for that matter. With that said, that's the time we had for today. See you next time.